Hello and welcome to lesson number 11, Inequalities. So, before we start about what inequalities are, let's first explore what equalities are. So, equalities are something of the form A equal to B. We don't really call this equalities, we just call these equations, but we say that A is equal to B. What this means is, what A equal to B means is, you already of course know, if A is some numerical value, then the numerical value of B is exactly equal to the numerical value of A. Both of them have the same exact numerical value. Here we can see on this number line, both A and B have the same exact value. If A is any other value, then B should still be that same value. Let's say A is this value over here, then B would be that exact same value. So there, what an equality A equal to B means is that the left hand side A's numerical value is equal to the right hand side B's numerical value. Similarly, there's another one that we have just the equal sign, that is the not equal sign. The not equal sign is written like this, and what this means is that let's say this is A and we have A not equal to B. If A is some certain numerical value like this, then B is all numerical values other than that specific numerical value of A. So here, if you don't know what this notation is, where I put like a circle with a hole in the middle over here, this is how we represent ranges in a number line. If you want to learn more about this notation of ranges, click this video on the top right over here. But for now, we're going to carry on. So here, this is what A not equal to B means. If A has some numerical value, then B can have any numerical value that's not that value of A. Similarly, of course, this also means that if B has some numerical value, let's say B is this numerical value over here, then A can have any numerical value that is not the numerical value of B. So basically, A and B do not have the same numerical value. This is the interpretation here. Unlike these, inequalities allow you some more freedom. An inequality is basically an allowance of a range. Let's take A greater than 2 and try to identify what this means. I'll actually put A in red so that we can see the range very clearly. A greater than 3, let's say. So what A greater than 3 is representing is all the values of A that are greater than 3. A can be any value so long as that value is greater than 3. Now in common mathematics, greater than is taken to be more in the positive x direction. So in this case, greater than 3 would not imply it is to the left of negative 3. It would rather imply only that it is to the right of positive 3. So if positive 3 is over here, that means A would be all the values excluding 3 to the right of 3. So here this is the meaning of A greater than 3. A can be any value so long as that value is greater than 3. There's another version of this where we have an equal sign as well, and that is A greater than or equal to 3. I will just use the same symbol because that's easier, so we'll still use the range 3. So what this means, what A greater than or equal to 3 means, is that A could be 3 as well, and it could also be any number greater than 3. So here the difference between the above and below two equations, the two inequalities, are the fact that the second one includes the point 3. So here, this point at 3 is also included in our possible values of A, and any other value that is also greater than 3 is also part of the possible values of A. So the difference between these two, the difference between A greater than 3 and A greater than or equal to 3 is that A greater than or equal to 3 allows A to be 3. You can see here by the fact that in the top distribution we have a hole at 3, in the bottom distribution we do not have the hole at 3. Similarly, we have another two symbols which are basically, these are first two symbols inverted, and those are, I'll use the same, actually we'll use a different number for this one. A less than, we'll put, let's say for the top one, we put A less than 2. Let's put A less than or equal to negative 1 just to have some variety. So over here, what we mean by A less than 2 is that given the value 2, A is some numerical value which is less than 2. And here, since we do not have an equal sign here, we do not include the exact point of a equal to 2. A is equal to all values to the less direction, which is the negative x direction, not inclusive of 2. So any values less than 2, which means we start at 2, then we go along the number line like this and end in negative infinity. So therefore 2 and 2 is excluded and all values less than 2 are included. So a has some value which is less than 2, non-inclusive of 2. A is somewhere to the left of the value 2. Similarly, over here, a less than or equal to negative 1, and of course here they have the difference. A less than or equal to negative 1, it means that a could be negative 1, in which case we need to put a shaded dot here, and all values that are less than negative 1. So all values to the left side to the negative x direction of negative 1. So we have all of this along the entire number line like this. A could be any of these values. So again, you can see all 4 symbols have their own unique meanings. A greater than 3 means that a is any value non-inclusive of 3 which is greater than 3. Here of course for the second thing, any value can be substituted for this second input here as well. It just means that a has to be greater than whatever is on the right hand side, non-inclusive of the right hand side in the first case. In the second case, a greater than or equal to 3 means that a could be equal to 3 as well, and a could also be greater than 3, one or the other. Here a less than 2 or a less than any value, again of course the right hand side can be any value. A less than 2 is all the values of a that are less than 2 and non-inclusive of 2. If you want to include that last value, then we could add a equal sign here as well. What this means is that a is less than or equal to the exact point as well, also possibility. In this case we have a less than or equal to negative 1, which means a could be negative 1 or a could be any value that is less than negative 1. So here these 4 have 4 unique behaviors, and I want you to perfectly understand what each of these behaviors mean. So I want to take your attention for a moment to direct you into how we reflect each of these expressions. Now what I mean by reflect is this. If we have that a is equal to b, then of course we can say that b is equal to a. Similarly, if we have that b is equal to a, then of course we can go in the reverse direction and say that a is equal to b. So a is equal to b implies that b is equal to a, and b is equal to a implies that a is equal to b. So this is a is equal to b if and only if b is equal to a, meaning that a being equal to b is sufficient to say that b is equal to a, and b being equal to a is sufficient to say that a is equal to b. To do a similar kind of reflection with inequalities, you have to do a little extra thing. You have to turn the symbol in the middle to a different symbol. So what I mean by that is, consider the statement that a is greater than b. What this means is that the numerical value of a is greater than the numerical value of b. So here we are saying that relative to the numerical value of b, the numerical value of a is to the positive x direction of the numerical value of b. What this means is of course that the numerical value of b is less than the numerical value of a. I think you can all agree that this statement is true. If the numerical value of a is more in the positive x direction than the numerical value of b, the numerical value of b must be more in the opposite direction or more in the negative direction. This is how we reverse these kinds of inequalities. To reverse an inequality, you need to reverse the sign as well. So if a greater than b, this implies that b less than a. Similarly, if b less than a, this also implies that a is greater than b. So we have this reversibility, the same reversibility we had with the equal sign, but unlike the equal sign, we need to change the sign in the middle as well. So if a is greater than b, it implies that b is less than a, and vice versa. Similarly, if a is greater than or equal to b, this implies that b is less than or equal to a. You can see that the equalness is preserved here, because of course if a is equal to b, then b is equal to a, which means if a is greater than or equal to b, then b has to be less than or equal to a. So the equalness is preserved. Similarly, if b is less than or equal to a, then of course that also implies in the reverse direction that a is greater than or equal to b. So we have that A greater than B implies B less than A, and vice versa. Similarly, A greater than or equal to B implies B less than or equal to A, and vice versa. So here, writing the other two statements, it's not really necessary because they are contained within this thing, but I'll of course write them just in case you don't see it. B less than A of course implies, my apologies, B less than A of course implies that A is greater than B. I'll actually erase this symbol in the middle, and I'll just only put the forward implication sign. A greater than B implies that B is less than A. A greater than or equal to B implies that B is less than or equal to A. B less than A implies that A is greater than B, and B less than or equal to A implies that A is greater than or equal to B. So here, if we want to reflect an inequality in the same way that we can reflect an equation, we must also remember to reflect the inequality sign. These inequality signs are of course designed so that we can easily do this. Here, what this symbol here is, the greater than symbol. It means that the thing on the left is greater than the thing on the right. You can also kind of conceptualize this by the fact that in the greater than sign, the left side is bigger, it's more wide open. On the right side end of the greater than sign is smaller, which means the thing on the right is smaller. Mirroring this thing, what we get is this symbol where the left side is small and the right side is big, meaning the left side is less than the right side, which is exactly what this expression means. So here, remember, you always need to reflect the sign as well if you are reflecting an inequality. So before we move on to the next thing I want to do, which is the negated equivalence of these signs, as we have equal and not equal to, there are also negated versions of the inequality signs, greater than or equal, less than, and less than or equal. So before we go to those things, I first want to talk to you about something called the trichotomy law. So the trichotomy law goes like this. Let's say that A and B are elements of the real numbers. For some A and B, we don't know what these A and B are, but we know that they are both elements of the real numbers. So considering this, let's say we have a number line, and let's say that A is this point here and B is some other point, let's say here. In this case, B, the point B, is in fact greater than the point A. If we move B somewhere else, let's say we move B over here. Now the value of B is less than the value of A. Let's say we move B, let's say somewhere else, let's say over here. Now B is greater than A. Let's say we move B right over here. Now what? Well, A and B are overlapping, so that means that A's numerical value and B's numerical value are equal, therefore A is equal to B. So here you will notice, no matter where along this number line I move B to, one of the three and only one of the three and exactly one of the three statements, A less than B, A greater than B, and A equal to B is true. Over here, A is greater than B, over here, A is less than B, and over here, A is equal to B. So, exactly one of these three statements is true. This fact, this principle, is what we call the trichotomy law. So, exactly one of the three statements, A less than B, A greater than B, and A equal to B is true. If one of these is true, the other two are false, and one of these is always true. This principle, the fact that if you have two real numbers A and B, one of these, exactly one of these, and only one of these is true, is what we call the trichotomy law. You cannot have none of these being true, and you cannot have more than one of these being true. Only one of these is true at any given time. So in this trichotomy law, since only one of these is true at any given time, for any two numbers A and B, element of the real numbers, we can derive the following. Let's now consider the opposite symbols, the not symbols of the ones that we previously discussed, the greater than sign, the greater than or equal to sign, the less than sign, and the less than or equal to sign. Their corresponding not operations would be the not greater than sign, the not greater than or equal to sign, the not less than sign, and the not less than or equal to sign. What I am going to attempt to show you is that the not greater than sign is identical to the less than or equal to sign. The not greater than or equal to sign is identical to the less than sign, and similarly the not less than sign is identical to the greater than or equal to sign, and the not less than or equal to sign is identical to the greater than sign. So we are going to have to use the trichotomy law to identify this, and I'll just draw an example over here. So let's say that we have that A over here is in fact not greater than B. So if A is not greater than B, it eliminates one of the two possible cases from our trichotomy law. Over here the three cases are that A is less than B, A is greater than B, and A is equal to B. So if A is not greater than B, this case is eliminated, which means we have only two cases left. Either A is less than B or A is equal to B. We have a single symbol that represents both of these cases together as a or statement, and that is the case that A is less than or A is equal to B, i.e. A is less than or equal to B. So therefore, without even having to draw a number line, we have the statement that A is not greater than B is identical to the statement saying that the value A is less than or equal to the value B. So here if we do draw this on the number line, let's say that this point over here is B. We just put some random point over here being B. So that means the values of A are not greater than the values of B. So all the values over here are not the values of A, meaning that the only values A could have are this value here, which is B, and all the values to the left of B, i.e. A less than or equal to B. So therefore A not greater than B is the same exact thing as saying that A is less than or equal to B. Similarly, if we do it for the other three, the next one we have to consider, of course, is that A, the value A, is not greater than or equal to the value B. Now, of course, here again, what we have to do, look at our trichotomy law and see which ones of these are invalidated. So if A is not greater than or equal to B, then certainly A is not greater than B, and also A is not equal to B. Eliminating these two from the trichotomy, the only other thing that can possibly happen is that A is less than B. Therefore, the correct other way to write the fact that A is not greater than or equal to B is A is less than B. So here we have A not greater than or equal to B, which is identical to saying that A is less than B. So here it's identical to saying that A is less than B. We can see this if we draw it in a number line. If B is, again we'll put some random value, let's say here, if B is this value, A is not greater than B, meaning A is none of these values, and A is not equal to B, meaning this dot is also invalid, meaning the only other possible things A could be is all the values less than B. So here this is A, which is identical to saying that A is less than B. So there A not greater than or equal to B is the same exact thing as saying that A is less than B. I'm not going to repeat this for the other two, but because I think you can already see the logical jump you have to make in order to get to there, but I'll simply state that A not less than B is identical to saying that A is greater than or equal to B. So this is identical to saying that A is greater than or equal to B. I'll quickly draw an example here. Let's say that B is this value over, let's make it somewhere here. A is not any value less than B, so A is none of these values, meaning the only values left for A are B itself and all the values to right of B, i.e. greater than or equal to B. Similarly, if we have that A is not less than or equal to B, what this implies is if A is not less than or equal to B, the only other possible thing that A can be is greater than B. So therefore, A not being less than or equal to B implies that A must be greater than B. So if this is over here, this is B, then A is all the values to the right of B. So here we actually do not need these not symbols because we already have these not symbols accounted for over with our normal symbols. So not greater than is the exact same as saying less than or equal to. Not greater than or equal is the exact same as saying less than. Not less than is the exact same as saying greater than or equal to, and saying not less than or equal to is the exact same as saying greater than. So we can swap these around. We don't really need these symbols, but you might see these symbols popping up sometimes in certain situations, in which case you must understand that saying not greater than is of course the same thing as saying less than or equal to, and the same for the other three as well. So here we really do not need those other four symbols, because they are already accounted for by the four symbols greater than or equal, less than, and less than or equal. So now on this basis, let's start deriving some identities for inequalities. Similar to equalities, where we had if A equal to B and B equal to C, these two statements are sufficient to imply that A is equal to C. We should know this. This is obvious. This is carrying through the equal sign. Similar to this, there's another thing in inequalities that also follows a similar pattern, but you must notice the key distinction between inequalities and the equal sign. We have that if A is greater than B and B is greater than C, this implies that A is greater than C. This is alright. However, if we have that A is greater than B and C is greater than B, this does not imply anything. This right here does not imply anything. Why not? Well, because all we have here is that A is greater than B, meaning A is somewhere to the right side, to the positive x direction relative to B. It's also saying that C is somewhere, now note my wording, somewhere to the right side of B. So that means that if we take a number line, let's say that this is the value of B. This means that what we mean by A greater than B is that A is somewhere along this line. What we mean by C greater than B is that C is somewhere along this line. But here, just because A is somewhere along this line and C is somewhere along this line, we cannot say where A is relative to C. So here you can see the underlying issue. We cannot say where A is relative to C. However, in the other case where we had A greater than B and B greater than C, what we had is, in that case, the relationship that looked like this. If we just draw it again, what we had in that case was there was some value C. Let's put C, let's say, over here. So this is C. And then relative to C, we knew that B was positive. So I'll actually erase this other thing because it's misleading. I'll erase this one and only go with the proper one, which is that A greater than B and B greater than C implies that A is greater than C. So what we had here in the first statement is, on the left, B was some value which is greater than C. So B is somewhere to the right of C. So let's say B is somewhere along this line. Along this line, let's say we know where B is. Relative to B, we also know that A is to the right of B. So now we can clearly see A has to be somewhere here. So if A is somewhere here, and that is definitely to the right of C, then A is greater than C. So therefore we can see that A is greater than C. Here we can think that this is a kind of a chain. We have the chain A greater than B who links to B greater than C. So if you write this as one expression, we can write it as A greater than B, which itself is greater than C. You can see there's a common chain here where all these signs are facing the same direction. Here also I should mention the thing that this implies that A is greater than C. However, if we have this thing, A greater than B and C greater than B, to write this in a chain, we would have to write something like this. You can see here in this chain, all the links are not facing the same direction. Here we have a greater than sign, but here we have a less than sign. Because this chain is incomplete, because all the symbols are not facing the same direction, we cannot imply anything from this. We cannot infer anything from this. This is simply a useless chain. In order to imply that the two ends of a chain are some relationship relative to each other, every single link within that chain needs to be the same symbol. So in this case, if we had instead A less than B, which itself is less than C, we can see within this chain all the links are facing the same direction. Therefore, A is less than C. So we are all good here. Similarly, and this is a finer point, if we have A greater than or equal to B and B greater than or equal to C, then we can say that A is greater than or equal to C. However, if we have this A greater than or equal to B, but then we have B greater than C, notice here this link is not the same as this link. Here we only have that B is greater than C. We do not have the implication that B could be equal to C. In this case, we can still imply something, but we cannot imply the full thing. We cannot imply that A is greater than or equal to C. What we can imply is only that A is greater than C. Why can't we imply that A is greater than or equal to C? Because in order for equality to hold, there needs to be an equal sign across this whole thing here. Since there is no equal sign across the whole thing here, since we've dropped an equal sign, we have the equal sign on the first symbol, but we do not have the equal sign on the second symbol, we can say that A is equal to C. In fact, A is not equal to C, because recall, B greater than C is the same thing as saying B is not less than or equal to C. So here, the not less than or equal to means that B is not also equal to C. So therefore, the equality cannot be carried through. However, the greater than-ness can be carried through. So here, this is a finer point. It is important for equality to be carried through. Every single symbol needs to have equality. If equality is not carried through, it means that at least one of the symbols does not have the equality. This of course is the same for the reverse direction. If we have A less than or equal to B, B less than or equal to C, this can be used to imply that A is less than or equal to C. However, if we have, let's say, A less than or equal to B, but B only less than C, then this of course implies only that A is less than C. We cannot imply equality here because we do not have equality between B and C. And of course, if you're wondering why I keep putting the less than sign without the equal here, no reason. This is also the same exact thing. If I have A less than B, B less than or equal to C, this also can only be used to imply that A is less than C. This cannot imply anything further. So that right there is how we make a chain and use the chain to express an inequality with a common point in the middle. If we have A greater than B and B greater than C, then we can imply that A is greater than C. Let's now move on to some other identities. The next one I would like to talk about is the identity that if we have A greater than B, this would imply that A plus C is greater than B plus C for any C element of the real numbers. This will work for any C element of the real numbers. It will also work for others, but for now we are only considering real numbers, so that's the case. We can easily prove for the real numbers with a simple number line. If we draw this simple number line and we say that B is some point here, then that means that if A greater than B, A is any point along this line here. If we do B plus C, and to do a plus C, let's say that we move the point B to the right by a certain distance C. Now B is over here. I'll call this point B plus C. We'll put the C in the yellow color. So you'll have a C here. We'll have a B here. This point here is B plus C right here. And the corresponding new range of A is this. And over here, what this is representing is A plus C. So we can see if A was greater than B, then A plus C is still greater than B plus C. So here, adding a constant to both sides of an inequality does nothing to the inequality's truth. The inequality is still of course true. This is of course the same exact behavior that we have for equations. If we have that A equal to B, then A plus C is equal to B plus C no matter what C is. Similarly here, if A greater than B, then A plus C greater than B plus C for any C. This is the same for the other three. I'm not going to write it out and draw it for the other three, but I'm just going to I will write it out for the other three, but not draw it for the other three. If A greater than or equal to B, then of course A plus C is greater than or equal to B plus C. And of course this is implied in the reverse direction as well. Each of these has its in the reverse direction as well. If A plus C is greater than B plus C, then A is greater than B. And similarly for the others, if A is less than B, this implies and has itself implied that A plus C is less than B plus C. Similarly, A less than or equal to B implies is necessary and required for A plus C to be less than or equal to B plus C. So in each of these cases, what we are seeing is that adding anything to both sides of an inequality, same as adding both sides to same thing to both sides of an equation, does nothing to the root of the equation. Inequalities in this case behave the exact same as equations do. One case where we do not get common behavior is when we multiply numbers. Here we have multiple cases. Let's say we have A greater than B. Let's say we have A greater than B. Given this, if C is an element of the real numbers and C is greater than 0, in this case, if we multiply both sides by C, AC would still be greater than BC. The reason for this is because C is positive, multiplying both A and B by C does nothing to the signs of A and B. The signs of A and B are still the same, which means that if A was some value greater than B, let's say B is over here, if A was some value greater than B, then we can have C times B and C times A, and we would still have the case that, let's put this in a different color, let's say this is C times B now, and in orange this is C times A. Still C times A is greater than C times B for a positive C. And here, by the way, the other set of symbols of course are valid. If A is greater than or equal to B, then and C is positive, then A times C is greater than or equal to B times C. Similarly, if A is less than B, then and C is a positive value, then A times C is less than B times C. Similarly, A less than or equal to B, then and C positive number, then A times C is less than or equal to B times C. So we have that. Where this doesn't work is when C is negative. If we have A greater than B and C element of the real numbers but C less than 0, in this case what we can then infer is that AC is less than BC. So you might notice here we are flipping the sign. Why are we flipping the sign? Because of this fact. This fact that a negative number reverses the number line. What I mean by this is, let's say we have B over here. Negative B is this point here. This is negative B. So if we have some constant C where C is a negative number, if C is a negative number, then C times B will be in the opposite direction that B is. So if we have A, similarly, if we have A, this is what we have when we have A greater than B. So then if we multiply these values of A by a negative number C, then what we will get, the corresponding values of C will be also negative, which means their direction will be flipped. So in this case, C times A will look like this. So over here we have A and we have A being greater than B. If we multiply both sides by a negative number, then the direction is flipped, and now CA is more towards the negative x direction compared to CB. So therefore, if we have A greater than B, then multiplying both sides by a negative number will give us that AC is less than BC. This is of course the same for the other three as well. All we have to pay attention to is the fact that if you multiply both sides by a negative number, the sign gets mirrored. Recall the mirroring from earlier. Similarly, if we have the greater than sign, it gets mirrored into the less than sign. If we have the greater than or equal to sign, it mirrors into the less than or equal to sign, and the same for the other two. So here it is important to note the mirroring effect. And of course there's the degenerate case. If we have A greater than B and C equal to 0, then of course AC is going to be equal to BC is going to be equal to 0. Multiplying both sides of an equation by 0 will of course give you 0 on both sides, and it's a destructive process. Multiplying both sides by 0 destroys any possible values, because all values multiplied by 0 will give you 0. So here note that if C greater than 0, meaning C is a positive number, then the sign holds. A sign of something, B, in this case A greater than B, will preserve when you multiply it by a positive constant C. So here we have A greater than B, which preserves into AC greater than BC. However, if C is a negative number, then the sign does not preserve and instead gets flipped. So here we have a greater than b. When you multiply it by a negative number, we get that ac is less than bc. And there's the degenerate case, the useless case, where if c is 0, multiplying both sides by 0 immediately drops both sides to 0, no matter what both sides are. A greater than b, a less than b, a greater than or equal to b, a less than or equal to b. Everything gets destroyed and we just get 0. So there we just get 0. Another useful identity is the identity of adding two inequalities together. So to do this, first let's go back to equalities, a equal b and such. If we have a equal to b and we have c equal to d, we can add these two equations, so to speak. We can say this equation is equation 1, we can say this equation is equation 2, and we can add them together. By what I mean by adding is adding the left hand sides and adding the right hand sides together to get the equation a plus c is equal to b plus d. This is a true statement. It's true because of the properties of the equal sign. If the left hand side of one equation is equal to the right hand side of that equation, and the left hand side of another equation is equal to the right hand side of that equation, then we can add the two left hand sides together, get a resulting left hand side, add the two right hand sides together, we get a resulting right hand side, and then say that a plus c is equal to b plus d. A similar process can be done for inequalities, however with some stipulations. If we have a greater than b and we have c greater than d, we can add these two equations and say that a plus c is greater than b plus d. In order to add equations like this, add inequalities like this, we need the same inequality sign to be in the middle here. A greater than b and c greater than d. These two inequalities add to the common inequality a plus c greater than b plus d. Similarly, if we have a greater than or equal to b and c greater than or equal to d, this can then be used to imply that a plus c is greater than or equal to b plus d. However, if we have a greater than b but we have c greater than or equal to d, again by the same way in where we had the other properties, if we have a chain when any link of the chain is not equal to the rest of the links of the chain, then we have an issue. Similarly here with the equalness, if a greater than b but c greater than or equal to d, this does not imply that a plus c greater than or equal to b plus d. This only implies that a plus c is greater than b plus d. For equality, we need every single link along the chain to be having an equal sign. Similarly over here, in order to have this thing to be adding both sides of the inequality, we need the same sign on all of these. However, of course, if all of them have the equal sign, then we can include the equal sign in the final statement. If not, we cannot. Similarly, for the other three, if we have that a less than b and c less than d, this of course implies that a plus c is less than b plus d. Similarly, if we have a less than or equal to b and c less than or equal to d, both of these have the equal sign, which means we can now imply that a plus c is less than or equal to b plus d. This is one set of identities, and for this, in order for us to carry down the equal signs, we need everything to have an equal sign. If not, we have to only have that we can guarantee the greater than or less than sign being valid. The equal sign requires every single term to have an equal sign within it. The next identity we have is somewhat similar but also different because it has certain rules. It only works in certain particular cases. If we have a greater than b and a and b both greater than 0, meaning a and b are positive numbers, and we have c greater than d where c and d are both positive numbers. In this case, we have that a is a bigger number than b and c is a bigger number than d, and all four of these numbers are in fact positive. Given this, then we can guarantee that AC is greater than BD. Now you might be wondering why I impose so many restrictions here. It's because if any of these numbers is potentially negative, we can get some strange or counterintuitive results. It's not really counterintuitive if you really think about it, but to your general intuition, if you think without actually thinking, if you just assume certain things, you might find that some results don't make much sense. For example, if we didn't have this condition, then AC could be less than BD. So here we are only going to talk about this case, the case where all four numbers are positive. If you want, you can explore the rest of the cases where certain numbers are negative and how they relate to this equation. But for A, B, C and D, which are all positive numbers, if A is greater than B and C is greater than D, meaning on the left hand side we have two bigger numbers and on the right hand side we have two smaller numbers, multiplying the two bigger numbers together will give us a number that is definitely bigger than multiplying the two smaller numbers together. Similarly, for the equality, if we have A greater than or equal to B and C greater than or equal to D, given the same restrictions of AB being positive and CD being positive, given these restrictions, then AC is greater than or equal to BD. Again, in order for us to have this, we need total equalness across every single one of the inequalities that we are using to produce this inequality. If this thing, for example, does not have the equal sign, then the final result cannot have the equal sign, because we cannot guarantee that the two multiplied together would equal the other two multiplied together. There's a few more identities we need to discuss, and those are the power identities and the inversion identities. So let's go to that one. So the inversion identities are as follows. Let's say that A is greater than B and all of these are greater than 0, meaning A and B are positive. Given this, A is a bigger number than B. A is a bigger number than B and A is a positive number and B is a positive number. Given this, if we do 1 divided by A and 1 divided by B, we do 1 divided by A and 1 divided by B. 1 divided by A means we are taking 1 and we are dividing it to a certain number of pieces, which is A number of pieces. On the right side, we are doing 1 divided by B, which means we are dividing 1 into a certain B number of pieces. If A is greater than B, this means that we are dividing 1 into more pieces when we divide it by A compared to when we divide by B. So then each piece of 1 divided by A is going to be smaller than each piece of 1 divided by B. Therefore, if A greater than B and both of these are positive numbers, then 1 divided by A is going to be less than 1 divided by B. Similarly, if A is less than B and both of these are negative, then what we have is two negative numbers and A is a bigger negative number than B is. So if we do 1 divided by A and 1 divided by B, here we are having a negative value of A and a negative value of B. If we do 1 divided by these, since A is a bigger negative number, 1 divided by A is going to be a smaller number, but it's going to still be a negative number. So then A being a smaller negative number implies it's more towards the positive direction, which means that 1 divided by A is more towards the positive direction than 1 divided by B. So therefore, 1 divided by A is greater than 1 divided by B. However, if we have that A is greater than B, but A is also greater than 0, but B is less than 0, what this means is that A is positive while B is negative. So then 1 divided by A and 1 divided by B, if we compare, 1 divided by A is going to have to be a positive number because A is a positive number. Similarly, 1 divided by B is going to have to be a positive number, so negative number, because B is a negative number. So then we are comparing a positive number and a negative number, which means that we have 1 divided by A, which is a positive number, which means it's greater than 0, and we have 1 divided by B, which is a negative number, which means it's less than 0. So in this case, what I'm trying to illustrate is the fact that you need to be careful when you have A greater than B. Just because you have A greater than B, this does not imply that 1 divided by A is less than 1 divided by B. This is not possible. We cannot imply this directly. Why? Because different things happen in different cases. As you can see here, clearly, different things are happening in different cases. In these two cases, we are all right. In the cases where both of them have the same sign, we have the expected result. If I instead rotate this second one around to have A greater than B, so as in this, which then now we have A greater than B, then 1 divided by A is going to be less than 1 divided by B. So we have this. So here we can see in both of these cases, if A greater than B, then 1 divided by A is less than 1 divided by B. In this other case, however, if one of them is positive and the other is negative, everything is now invalid and we can no longer say that A greater than B implies 1 divided by A less than 1 divided by B. So I encourage you to take this with caution, and remember, the only way that you can do A some sign B is implying that 1 divided by A and 1 divided by B have some other sign in the middle is only if both of them have the same sign. If A and B are both positive or A and B are both negative, then you can do the 1 divided by A thing and flip the sign in the middle. However, in the other case, if one of them is positive and the other is negative, take caution and check that first, because if one of them is positive and the other one is negative, then we have that A greater than B, and of course that would also mean that 1 divided by A greater than 1 divided by B. So look out for that. You could get tripped up with that situation there. We're going to look at one more situation, which is taking indexes, where you take some power of both sides. So again, let's just take a general thing. Let's say A greater than B. This of course works for all the signs. If we have A greater than B and we have n being some value greater than 0, then A to the power of n is going to be greater than B to the power of n. Similarly, A to the power of negative n is going to be less than B to the power of negative n for any positive n. This is of course the same for the other three symbols. If we have the greater than or equal sign, less than or equal sign and all of that, we can still imply this. So that's the end of our identities. We don't really have all that many other things to talk about in this lesson, just a few. That is how we use inequalities when we are dealing with functions. So we'll go to that, but for now we are done with all the identities within this lesson. So there are only a few more things to talk about other than the identities, and those things are the modulus function, conditional functions, where we have a function being one value based on a given condition and different values based on different conditions, and finally we have to talk about when we have an inequality sign between two functions. So let's start with the first of those, which is the modulus function. The modulus of x is a special function which is defined in this way. It is defined as x for x greater than or equal to 0. So what this means is that if x is greater than or equal to 0, in that case our output will be x. It is then defined as negative x for x less than 0. So in this case, if we have an x that is less than 0, let's say negative 2. If we want to take the modulus of negative 2, we will have to do the second operation, because x is in this case less than 0. Negative 2 is less than 0. So in that case the return will be negative x. So that means negative 2, which is 2. The modulus function returns us the size of the number that we place into it. In higher dimensions the modulus has different meanings, but for a simple one-dimensional representation, you can think of the modulus as the distance, the absolute distance away from the origin or 0 of a certain number. In this case, we have the distance of negative 2 from 0, which is 2. It is 2 in the negative direction. We can see this, of course, if we just draw the number line. This is negative 2. The distance of negative 2 from the origin 0 is simply 2. 2 in the negative direction, which we would draw with an arrow like this. So it is negative 2, but it is 2 going in the negative direction. And the modulus function returns this value. So this is how it's defined. The modulus of any input gives that input if the input is greater than or equal to 0, but it gives the negative value of that input if the input is less than 0, which means it will basically give you the size of the input that you put into it. Similar to this, we can have other functions that operate differently based on their inputs. This is one example of such a function. Such functions are known as piecewise functions. Here, the modulus function is a piecewise function because it has one behavior for certain values of x and has a different behavior for certain other values of x. In general, a piecewise function is defined as something like this. fx equals, and then it is expanded out into different cases. Here we have one case which we separate with a colon into its condition. Here we have another case which we separate with a colon into its condition, and we can do as many of these as we want and give as many conditions as we want. The only condition that we need here is that these conditional statements should not overlap with each other. What I mean is something like this. Let's say fx is for let's say it is x squared and x cubed. It is x for certain value, let's say for x's less than 1. It is x squared for x's between 0 and 2, and it is x cubed for x's greater than or equal to 2. So here within this there is an issue. Here we can see this is for all the x's less than 1, and here this condition will be applied for all the x's between 0 and 2. If I draw this out on a number line, I draw the two ranges corresponding to the first two. If I let's say first one is represented by purple, the second one is represented by red. Purple is all the values of x which are less than 1, which means we go from the value 1, I'll also mark 2 because I need 2 later. We go from the value 1, non-inclusive of 1, all the way down to negative infinity. So this range is going like this. How about the red range? The red range goes from 0 non-inclusive, so here, up to 2 non-inclusive, so here, and then all the values in the middle. Here we can see an issue. These two ranges are overlapping. The purple range and the red range are overlapping within this area from 0 to 1. Due to this issue of an overlap happening, here this is not a valid piecewise function. We cannot have a piecewise function where two different answers could be given for a certain range. In this case, this output and this output could both be given for this range from 0 to up to 1. So the 0, x is between 0 and 1. For this range, both of these conditions are true, which constitutes a problem. We can have cases where certain values are not defined. For example, the square root function is such a function. The square root of x is equal to the positive square root of x only when x is non-negative. So this is the square root function is defined only for x's which are greater than or equal to 0. For x's less than 0, of course, for the negative numbers we have the complex numbers, but within the real numbers the square root of x is defined only for x greater than or equal to 0. Similarly, we can have other functions which are not defined for certain values. Let's say gx, which is 1, let's say 2x plus 1, and let's say x squared. It is 1 for any x between negative 3 and 0, let's say, just some random range. It is also 2x plus 1 for x's between 1 and 2 inclusive, and it is x squared for x's greater than 2. So we have this. So in this set of conditions, you might notice there is no condition that is valid for x's between 0 and 1 inclusive. There is no valid values for x's between 0 inclusive and 1 inclusive. Similarly, there is no valid expression for x's less than negative 3. So for x less than or equal to negative 3, there is no valid expression. The rest of the number line is covered, however. So here, if we represent what's covered, if I put some other colors to this thing, let's say this color is blue, color corresponding to this one is going to be orange, and the color corresponding to this one is going to be just green. Here, if I draw the blue range, I'll draw the points that are relevant here. -3 is relevant, 1 is relevant, and 2 is relevant. In this case, the ranges we have that are valid here are a hole here, a hole here. This range is valid, and then from 1 to 2 inclusive, 2 inclusive is valid. So here 1 exclusive, 2 inclusive is valid, and then after that 2 exclusive and upward is valid. So this range is valid. So you can see here we have some invalid ranges. This range there's nothing, and this range there's nothing. This is perfectly acceptable. It is perfectly acceptable for a function, a piecewise function such as this, or some other function, to be undefined at certain values. What is unacceptable is what we saw previously, where two functions are overlapping within the same range. We cannot have this being allowed. So that's what a piecewise function is, and this is the condition that you need for a piecewise function. Its conditionals should not overlap, meaning there should not be two possible values for a given input. However, there can be certain inputs for which there is no value. That is totally fine. And finally, regarding inequalities with functions, let's consider, let's say, p of x and q of x. Let's say p of x is x squared plus 1 and q of x, let's say, is 4x plus 7. And let's say we want to find for which x's p of x is greater than q of x. How would we do this? Well, we can just substitute the functions in and say if px is greater than qx, then x squared plus 1 must be greater than 4x plus 7. Alright? This still doesn't solve our problem. We still have something that we do not have in terms of which values of x this will be valid for. So now we can keep solving. One thing we can do in this case, since we have a quadratic, what we can do is take everything to one side, in which case we get x squared plus 1 minus 4x minus 7 greater than 0. Recall that this is still valid because adding a constant to both sides does nothing. So in this case we've added a 4x to both sides and we've added 7, adding any value to both sides does nothing. Here in this case we've added a 4x, negative 4x and negative 7 to both sides. So now we have x squared plus 1 minus 4x minus 7 greater than 0. If we simplify the terms, what we get is that x squared and then minus 4x minus 6 is greater than 0. So this means, this kind of solving means that whatever values of x for which this is valid, the inequality up here is also going to be valid. So if we can just figure out for which x this is valid, we can find out for which x this is valid. So now here at this point, what we can do is try to find for which x's this thing is equal to 0 and then find in terms of that to which directions of these zeros is this function valid. So what I mean by that is this. We want to find for which x's this expression is greater than 0. Instead, let's try and find for which expressions for which values of x this expression is equal to 0. So doing this, we know how to do this. We have a quadratic here, x squared minus 4x minus 6 is equal to 0. Here the values of x for which this expression is equal to 0 is negative b, which in this case is 4, plus or minus the square root of b squared, which is 16, minus 4ac, which is minus 4 times 1 times negative 6, divided by 2a, which in this case is 2. So the two values of x for which this thing is 0 are, if we do the calculation, 4 plus or minus the square root of, in this case we have 4 times 6 is 24, 24 and then there's a minus and a minus, which means it's a plus 24, 16 plus 24 is 40. So it's 4 plus or minus the square root of 40 divided by 2, which is 2 plus or minus root 10. So the two values for which this x is going to be expression is going to be 0 for x are when x is 2 plus root 10 and 2 minus root 10. So over here we have 2 plus root 10 is somewhere here. If I just write 2 plus root 10 is somewhere over here, and 2 minus root 10 is somewhere over here. So here at these 2 points, 2 minus root 10 and 2 plus root 10, at these two values of x, the expression here is equal to 0. If we can find within this area what x is, what x squared minus 4x minus 6 is, within this area and within this area what x squared minus 4x minus 6 is, then we can solve our inequality. So the property we are going to use to solve this particular case is the fact that quadratics are either increasing like this continuously or decreasing like this continuously with either a local minimum or a local maximum. We cannot do this for higher order functions, and instead what we have to do is compute the derivative. But for order 2 functions, we can easily do this generalization. We know for any quadratic function, it is either sloping up or sloping down with either a minimum or a maximum. So in this case, this function is sloping up. How do I know this? It is this kind of shape because the coefficient of x squared is a positive number. It's 1. Meaning that as x gets really big, x squared is going to get really big. Since x squared is multiplied by a positive number, it's going to get really big. Similarly for negative x's, because a negative number squared is a positive number, and because the coefficient of x squared is 1, meaning it's a positive number, it's going to go to positive infinity on that side as well. So therefore, if this point here is 0, and at this point here we have 0, i.e. this is the x-axis, then for all the values in the middle, this is going to be negative, and for all the values to the left hand side and the right hand side, it's going to be positive. Therefore, by this observation, I can say the values for which this expression is valid, which I'll mark with a red color, are going to be these values here and these values here. For higher order equations and inequalities, we don't actually have the tools necessary to solve them within the syllabus. We only have up to second order here, but this is how you solve a second order inequality of two functions. You try to take it and turn it into a quadratic, and once you turn it into a quadratic, you find for which values of x it's going to be 0. Then you have to do some extra reasoning to figure out, alright, it's going to be equal to 0 for these values of x, and then after that, for further values of x, which values is it going to be positive for and negative for? In this case, because our function that we arrived at, this function here, is going to be an increasing function, and we want to find the values for which is greater than 0, it's going to be all the values to the right hand side of the higher root and all the values to the left hand side of the lower root. So that's the kind of reasoning we have to do. It's much simpler for linear ones, which is why I didn't actually do it. We'll do a linear function comparison right now as just for completeness. Let's say r of x is some linear function and s of x is some linear function. Let's say 4x plus 2 and 2x minus 7. So in this case, let's say I want to find r of x greater than or equal to s of x. In this case, I can subtract s of x from both sides. I'll substitute first. I'll get 4x plus 2 is greater than or equal to 2x minus 7. Removing 2x minus 7 from both sides, I get that 4x plus 2 minus 2x plus 7 is greater than or equal to 0, which we can then simplify into 2x plus 9 is greater than or equal to 0, which we can then rearrange to get that 2x is greater than or equal to negative 9. So then x is greater than or equal to negative 9 divided by 2. Therefore, these are the values of x for which this expression is valid. Here it's much simpler than when you have to do two quadratics. For two linear functions, it's very simple. You just equate them using the inequality, and then you use the inequalities identities to clean up one side and make it 0, and then try to isolate x and find what values of x for which the expression is valid. For the quadratic, of course, we have to use a more complicated method such as this, where we find for which values we are equal to 0, and then consider the expression that we have and what happens to the right side of 1 0, what happens to the left side of 1 0, and then finally for which values of x this equation is valid. So in this case, what we have is for all the x greater than 2 plus root 10 and for all the x less than 2 minus root 10, this expression is valid. If I write this in terms of a set notation, this is x elements of the set of all x's that are going from negative infinity all the way up to 2 minus root 10 exclusive union with all the x's that are going from 2 plus root 10 exclusive all the way up to infinity. We do not have to deal with any higher order inequalities of functions, but we do have to deal with certain functions where we have moduli, and in that case there's an extra bit of work that we need to do. This is not really standard as in systematical, it's just an explanation of what kind of things that you can do in order to get the solutions. This is not exactly the way you have to do it, this is just a way you have to do it. You can do it. So consider a modular function's expression such as this. The modulus of x minus 3 is greater than 2x plus 1. This is a modular function, meaning that for certain values of x, the function behaves in one way, for certain other values of x, the function behaves in a different way. In this case, the modular issues we have are with the values of x in this expression here. Here we have that x minus 3's modulus is being taken. So here this internal thing will be positive for x's greater than 3, because if x is anything less than 3, this thing is not going to be positive, it's going to be something else. In this case, because the modulus is inclusive of 0, we can do the x greater than or equal to 3, for which this expression is going to be positive. For others, this expression is going to be negative. So when it's negative, it's going to be negative for x less than 3. In that case, there's a different behavior. So we can split this into two different cases. The first case is for x greater than or equal to 3, and the second case is for x less than 3. And for each of these cases, we can evaluate the function's behavior and solve for the values of x for which it's valid. So here, for the first thing, when x is greater than or equal to 3, recall that the modulus function is going to output itself for when the value inside of it is going to be positive, i.e. the absolute value of x is equal to x for x greater than or equal to 0. So in this case, if the internal function is positive, i.e. x is greater than or equal to 3, then we are just going to have x minus 3 being greater than 2x plus 1. Solving this in the normal way, what we have is that negative 2x plus x, and then minus 3 minus 1 is greater than 0, which is negative x minus 4 greater than 0, meaning that negative x is greater than 4, meaning that x is less than negative 4. Notice here what I did, I multiplied both sides by negative 1. Recall that if you multiply an inequality by a negative number, you need to swap the two sides of the inequality. So this gives us that x has to be less than negative 4. So here what this means is that for x's greater than or equal to 3, x needs to be less than negative 4 in order for this equation to be satisfied, which is impossible. Why is it impossible? Because in order to get to this point, we had to first assume that x is greater than or equal to 3. For x greater than or equal to 3, it is impossible for x to be less than negative 4. In which case this expression here is invalid. For the other case, for x is less than 3, what we have is the negative value of the internal of the modulus, which in this case is x minus 3. So we have negative x minus 3, and it has to be greater than 2x plus 1. So what we really have is negative x plus 3 being greater than x plus 1. 2x plus 1, my bad. Taking the whole thing to one side, we can see negative x minus 2x plus 3 minus 1 has to be greater than 0, i.e. negative 3x has to be greater than, in this case if we take this thing, this is 2, taking to other side is negative 2. Multiplying both sides by negative 1, we can see that 3x has to be less than 2, i.e. x has to be less than 2 divided by 3. So here, this range here is valid, because when we assume that x was less than 3, we found a corresponding result that is also less than 3. So here, this in this case is valid. Here this illustrates the fact that there can be invalid cases, such as this right here. For x is greater than or equal to 3, we found a result where x is less than 3, in which case this result is invalid. Do not go writing this as a valid answer, because it is actually invalid. Here, x less than negative 4 is the result we got when we assumed that x was greater than or equal to 3. Those two things cannot happen at the same time. Therefore, this is invalid. On the other side, however, we have a valid thing. X can be less than 3 and less than 2/3 at the same time. And because both of these need to be true in order for the expression to be true, we need to take the overlap of the two. Considering the two expressions we have here, we have x less than 3 and x less than 2/3. If we consider the two, x less than 3, x less than 2/3, the first expression is going from 3 all the way down like this. The second expression is going from 2/3 and all the way down like this. Considering these two and which ones of them overlap, we can clearly see these two things overlap for all x's over here. So therefore, the overlap of the two is all x's that are less than 2/3. So the final result is that x is less than 2 divided by 3. This is the final result for this expression here. Note, the only things we did specially here is to consider the positive cases for the functions inside the modulus separately and the negative cases for the functions inside the modulus separately. When we consider the two separately, we got a bunch of different cases. Be warned, however, it can get more complicated than this. For example, we could have two moduluses. Within the syllabus, we don't really go beyond two moduluses, but if we had more than two moduluses, we had to consider even more cases. However, for the case where we have just two moduluses, let's say we have 2x plus 1 and x minus 6. In this case, there are four possibilities that can happen here. The four possibilities are this thing being positive, this thing being positive, and this thing being positive, this thing being negative, and of course this thing being negative, this thing being positive, and both of them being negative. So we have positive, 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 negative, negative, positive, and negative, negative. It should be noted that some of these cases do not exist. We will do it for this simple example. I will not solve for the final answers of x. I can leave that to you as an exercise, but I will show you that some of these ranges are not valid and for which ranges we have to consider. For the first thing, considering absolute value of 2x plus 1, this thing is going to be positive for some values and negative for some values. 2x plus 1 is going to be positive for some values and negative for some values. 2x plus 1 is going to be positive when x is greater than negative a half, because we can see if 2x plus 1 is greater than 0, this implies that 2x is greater than negative 1, which then implies that x is greater than negative half. So therefore, this thing is going to be positive for x greater than negative a half. So, and we have to include the 0 of course, because that's how the modulus works. So this is going to be positive for x greater than or equal to negative half, which means it's going to be negative for x less than negative half. Similarly, for the other function, x minus 6 is going to give us a positive value for certain numbers and negative value for certain numbers. If x minus 6 is going to be greater than 0, then x has to be greater than 6. So therefore, it's going to be greater than 6, but we have to include the 0. Therefore, this value on the inside is going to be positive for x is greater than or equal to 6. So therefore, it's going to be negative for any values of x that are less than 6. So we have this. Note, in this case, there are certain overlaps. You can see here, if we draw the two in number lines, we can see a certain overlap. I'll call the first condition, we'll put some colors so that we can easily see them. The first condition, I'll call this thing blue, and this thing may be red. Then for the second condition, I'll call this purple, and I'll call this one orange. So here we can see for the first one, the point of interest is negative half. If I draw negative half over here, for x's that are greater than or equal to negative half, we have one thing, so that is inclusive. So I'll put a dot there to show the inclusiveness and everything to the right here. And for the red one, it's exclusive of the point negative half and everything to the left. Similarly, for the purple and the orange, what the point of interest that we have here is positive 6. Everything to the right, including positive 6, is going to be belonging to purple, and everything to the left of positive 6, excluding positive 6, is going to be belonging to orange. Here we can see within this, there are certain overlaps and there are certain places where we don't have overlaps. Over here, for this range here, we can see there's an overlap of orange and blue. So here what we have is an overlap of blue and orange. We have blue and orange overlap. We also have blue and purple overlap. So we have blue orange and blue purple, i.e. we have plus minus overlap and the plus plus overlap is happening. These two overlaps are happening. How about the other two overlaps? Well, red is overlapping with orange, but red is not overlapping with purple. So therefore we have the minus and minus overlap, but we do not have the minus and plus overlap. This overlap is missing. You can see here clearly one of the overlaps never actually happens within this function. The other three of course happen, which means we need to consider these three and each of their cases separately. So here, these three cases, if we consider their ranges, we can see that this case, the plus plus case, is going to happen for all x's that are greater than or inclusive of 6. So here, if I dot this out, for all of these values, this case, the plus plus case, is going to happen. considering the other case, the plus, I apologize, I've marked the wrong one. The plus case is this case here, the second case. It is going to happen for all x's greater than and inclusive of 6. The other case up here, which I'm going to mark with yellow, plus minus case is happening for all values of x excluding the value 6 and including the value of negative a half. So here we have to include the value of negative a half. If I draw a dot like this, all of these values are belonging to the yellow case. Similarly, if we consider the third and final case, which is, I'm going to mark it with green, this case, the negative case, this case is all the values of x from negative half exclusive all the way down to negative infinity. We do not have this other case here. This case, the negative positive case, is non-existent within this range. So here, if you are going to solve this, what you have to do, consider each of these three cases separately. Within these cases, solve for the values of x. Make sure the values of x are within the values that you assumed in order to get those values, and finally write those as the solutions for this equation. So that is all for this episode here today. You might have felt that this video was slightly rushed, and it was slightly rushed. However, there's a lot to discuss and I do not have time to discuss everything. So I'm actually going to do probably a part 2 to this video, or an addendum to this video, as in an additional part to this video, which I will do and publish soon. So that is it for this lesson. There will be an addendum on how to do modular comparisons of two functions with inequalities and how to solve quadratic equations with inequalities. But for now, thank you for watching and goodbye.